Welcome to today's online class, children. In the previous class, we have seen about the types of semiconductor, that is intrinsic semiconductor. An intrinsic semiconductor is a pure semiconductor, and what about the energy level, how the crystal structure, everything we have seen. And also what are all the limitations of intrinsic semiconductor also we have seen. Okay, because of that we need to go for it is a pure semiconductor, so the actually it is of not practical use is very less. That is why we are going for actually doping deliberately. We are making the semiconductor impure by adding some impurities, that is specific impurities, that is p-type impurities like pentavalent or trivalent impurity to be added to the tetravalent intrinsic semiconductor, that is silicon, germanium, whatever is that. Okay, therefore now that everything we have seen in our previous class. Now we are going to see this extrinsic doped semiconductor is what is called extrinsic semiconductor, which is an impure semiconductor. And this extrinsic semiconductor, there are two types. One is what is called N-type semiconductor, and the other one is what is called P-type semiconductor. Okay, in the case of, now we are going to see both. First we'll start with N-type semiconductor. In the case of N-type semiconductor, see, actually I told you already some impurity will be deliberately added. Okay, so here to the tetravalent silicon or germanium semiconductor, a pentavalent impurity is added. Pentavalent: arsenic, actually phosphorus, antimony, bismuth, etc., like that. They have 5 valence electrons, and it is added to the pure semiconductor, that is an intrinsic semiconductor. And what happens because of that? There will be, because it is having pentavalent, means 5 electrons are there. Of this 5 electrons, what happens? Because I told you what are, the impurity, the size of the impurity, what are the conditions? Size of the impurity atom should be same as that of the semiconductor atom, so that it should go and replace the portion of silicon without changing the atomic structure of the semiconductor. And also I think I told you only one part of impurity, that is pentavalent impurity here in the case of N-type semiconductor, pentavalent impurity is added to silicon, tetravalent silicon or germanium. Okay, whatever is the semiconductor, only one part in million part of semiconductor atom, one part of pentavalent atom to be added to million parts of tetravalent semiconductor atom. You cannot, just like that, you cannot add as you like. Why? Because it has to be added in a controlled manner, so that the characteristics of the semiconductor is not actually distorted. Okay, so that is very important. Now I think this here, when arsenic, see here I have arsenic. Okay, arsenic is added. Then what happens? Arsenic is a pentavalent impurity, therefore it has 5 electrons, valence electrons, of which 4 valence electrons, see here, 4 valence electrons, here it is actually forming a covalent bond with the nearby silicon atoms, with the nearby silicon atoms. Okay, therefore, okay, that is fine. Therefore, 4 of which it has 5 pentavalent, of which 4 are engaged in formation of covalent bond with a nearby silicon atom. And apart from that, it has one more. That one more atom is now it is free. This one more atom here, it's not one atom, it is one more electron is free. It has 4, it is electrons, 4, it is a pentavalent impurity, it has 5 electrons, of which 4 are engaged in forming the covalent bond with the nearby silicon atom, and 1 electron is free. And this electron is almost free. How do you say? See here, because the bonding, this electron is weakly bound to this parent arsenic atom. Why? Because you know that there is a electrostatic force of attraction between the electron and the, what is that, atom here. Because and what is the binding energy with the new, if you want, see here it is revolving, and here these electrons, actually the binding of the electron, because it is weakly bound to that atom. Why? What is the reason for that weakly binding? Because you know that the force of attraction, okay, like a Coulombic force of attraction, is nothing but 1 by 4 pi. Okay, here not epsilon, not epsilon for silicon. Epsilon, that is what is the permittivity of silicon if it is a silicon. Okay, silicon, and Q1 Q2 by R squared. What is Q1? Q1 is Q1 Q2 by R squared. Okay, what is Q1? Q1 is the charge of this arsenic atom, and this here arsenic, that is ion, because one, and this is the electron, free electron. Therefore Q2 is the free electron. And what is the boundation now? The boundation between the parent atom and the revolving electron here, okay, it is actually almost free. It is, there is no bonding here for that fifth electron. 4 electrons are actually forming covalent bond. The fifth electron only we are talking about. The fifth electron is loosely bound with the bound to the parent arsenic atom. Okay, therefore arsenic is pentavalent, right? Therefore what happens there, why it is loosely bound? For that only, F is equal to 1 by 4 pi epsilon silicon, that is permittivity of silicon. Okay, if it is nothing, is a vacuum, means epsilon naught. But here everything is silicon here. If the atom is in the pool of silicon, therefore what is the medium here? Silicon is a medium. Therefore silicon, if you say K epsilon here is nothing but, it is very, very large. The dielectric constant of silicon, that is nothing but, if you want, F, that is equal to 1 by 4 pi K into epsilon naught into Q1 Q2 divided by R squared. Therefore here epsilon naught is nothing but permittivity of free space. Okay, and K is the dielectric constant of silicon. Dielectric constant of silicon is of the order of 11.7. Okay, so 11.7. Therefore, which means that, see, the force between the bonding between the electron, free electron, the fifth electron, and the arsenic atom here is highly, it is now, what is that? It is very, very less. It is very less. Why? Because of the dielectric. It is in the pool of silicon atom. Therefore silicon has a dielectric constant 11.7. Therefore the bonding has become very, what is that, bonding between the electron and the arsenic become very less. So which means they are almost free, no more. Well, little energy of the order of 0.045 electron volt. Okay, this much in a 4-5. Therefore 0.045 electron volt, if it is given to this electron readily it will jump to the conduction band. Are you following? Therefore that much free the electron is. Okay, therefore only very, very feeble energy, the energy you see 0.045 electron volt. That is for silicon, because we are dealing here with silicon. If it is germanium, and even it will be still less, 0.01 electron volt for germanium. If germanium atom, if the pentavalent impurity is added to germanium atom, then even less amount of energy, 0.01 electron volt of energy is required for the electron, these free electron, to jump into the conduction band. That will be completely free, so that they will be available for conduction. Are you following? Therefore, now what happened? The arsenic, this pentavalent impurity, that is actually donating one free electron. It is donating one free extra electron. Why extra electron? If our you see, in the case of intrinsic semiconductor, there will be at room temperature. I am telling we are dealing here with at room temperature. So some of the electrons will jump from the which band? The valence band to the conduction band. right? So when they are jumping from valence band to conduction band, there will be some holes will be produced in the valence band, and there will be the equal number of electrons will be produced in the conduction band. This is the intrinsic characteristics, correct? Intrinsic characteristic. That is here also it is there. It is there. In addition to that, carriers. That carriers is always available. Why? Because definitely at room temperature, many of the electrons will be from the valence band. They will jump into the conduction band as usual, as like your intrinsic character semiconductor here also that is there. But in addition to that, arsenic is added. Arsenic gives you one more. What is that electron? One arsenic atom is added means one extra free electron is there given for conduction. That is the difference. In the case of intrinsic, only Ne is equal to NH. But here, when arsenic is added, when a pentavalent arsenic, phosphorus, antimony, bismuth, whatever is that, when it is added, pentavalent impurity is added, one extra electron it is getting. One atom gives one extra electron. Are you following? Therefore, this electron, therefore, which means that this arsenic is donating one electron. No, therefore, they are called as donor impurities. They are called as donor impurities. Very important. Why? Because their electron, out of which 5 electron, 4 electron is forming the covalent bond, 1 electron is given for conduction. Okay, you take. It is going to conduction band. How much energy is required? This much, 0.045 electron volt energy if you are giving. Therefore, definitely, what is even at the room temperature? Even at room temperature, therefore, it will be jumping from valence band to conduction band. Hence, okay, why? Because thermal at room temperature energy, thermal energy, it is of the order of 0.025 to 0.03 electron volt only. So, okay, therefore, what happened? Therefore, definitely even at the room temperature, comparable, this energy is very much comparable to, what is that, thermal energy, a slight more, let it be, okay. Therefore, even that, so many electrons will be jumping, what is that, not so many electrons, that is as many number of donor atoms, okay, extra electrons will be available in the conduction band for conduction. So which means that here number of electrons here, why in if it is intrinsic means Ne is equal to NH. Here also there will be some electrons that is jumping from the valence band to conduction band, but in addition there are some electrons that is donated by the pentavalent impurity. Therefore, you will be getting more number of electrons in the conduction band than that holes in the valence band. That is the very important characteristic of this N-type semiconductor. N-type semiconductor, when you are adding a pentavalent impurity, so what happens? Number of electrons in the conduction band, because these electrons will be loosely, the pentavalent 50 electron is loosely bound, a slight energy is given to it, then immediately it will go to the conduction band. Therefore, there it will be available for conduction. Therefore, total number of electrons in the conduction band will be definitely more than the number of electrons, number of holes in the valence band. Okay, therefore, conductivity here is dominated by electrons. Correct? Why? Number of electrons are more here. Okay, negatively charged. Therefore, conductivity here, which is dominant here, negatively charged. Okay, electrons. Electrons are only dominant here. They are majority carriers of electricity. Okay, but in the case of what is a pure semiconductor, both will play the same role. Okay, Ne is equal to NH, but here Ne is more than NH. Therefore, negatively charged electrons are called majority carriers. Are majority carriers of electricity. Are you following? Therefore, that is why it is called N-type. Negatively charged are dominant. Electrons are dominant. That is why it is called N-type semiconductor. Negative charge is the majority carriers here. Okay, therefore that is called N-type semiconductors. Are you following? Therefore, now that is very, very important here. In addition to, therefore here number of holes will be there. Why? Because number of holes are produced because of thermal energy jumping from valence to conductor. In addition to that, the donor impurity has given extra electron. Therefore, number of electron is more in conduction band than the holes in the valence band. That is why it is called donor type semiconductor, or it is what is called N-type semiconductor. Donor type. Why donor type? Because it is donor atom. Donor impurity is donor impurity. The impurity here is a donor impurity. Are you following? Therefore, this is about what is that? How the crystal structure, how it is, the electrons are extra electron, pentavalent impurity, one electron is used, okay, in for conduction, right? Now, like that, the same thing, if I want to draw with a energy band diagram, okay, therefore you see here, here this is your, see, here, this is, okay, I have a, okay, it is conduction band and this is the valence band, okay, and you see here, if I want, see here, these are all many energy levels, and here, see what is the difference between the intrinsic and the extrinsic semiconductor energy band diagram. You see here, you know that here the holes, because there will be holes here. Why? Some of the electrons from the it is a valence band and this is a conduction band. Some of the electrons from the valence band, it will go and it will occupy the conduction band. Okay, so I have drawn here 4. Okay, right. So this is the intrinsic characteristics. But what happens when you are adding a donor impurity? What happens here? With respect to, I have explained with respect to crystal structure. Now with respect to energy band diagram, once you add the donor impurity, what happens? One extra energy level will be created. Listen very carefully. One extra energy level will be created just below the conduction band. Extra energy level will be created just below the conduction band. Okay, and there all this donor impurity has donated the electron, no, all will be here. How many number of donor impurity is added? That many number of free electrons will be here. Where in the extra energy level created, that energy level is what is a donor energy. Donor energy level or a state, whatever. It is a donor energy level. Why? Because of that electrons, all the, see, I told you the electrons, every impurity atom is donating 1 electron. Where the electron will lie? All these electrons, they lie in this donor energy level, which is created just below the conduction band. Okay, now very easy. What is the gap between these two? Donor energy level and the lowest energy level of the conduction band here for silicon, it is 0.045 electron volt for silicon, and for germanium it is 0.01 electron volt. This many, very, very small gap between the donor energy level and the lowermost energy level of the conduction band. Okay, very, very less. So what happens? These electrons readily, what it will do? It will now jump now. That is, little energy is only required now. So just like that, they can go into which band? Conduct. It is very easy. This little amount of energy is given because they are situated in the specially produced energy level, what is called donor energy level. So all these extra electrons which are donated by pentavalent impurity, all are actually situated here in this energy level. Once small energy is given, immediately they will go to the conduction band. As they go to conduction band, therefore what happens? Number of electrons in the conduction band will be more. So you see here, number of holes in the valence band is less when compared to the number of electrons in the conduction band. Therefore this is very, very important. Creation of donor energy level in the case of N-type semiconductor. Okay, and next one I think I want to tell you about Fermi energy level. See, in the case of Fermi energy, in the case of intrinsic semiconductor, Fermi energy level will be exactly half the way between the conduction band and the valence band. I think we have seen in the previous class. But now, what is Fermi energy level? It is the energy level corresponding to the center of gravity of conduction electrons and holes when weighed according to their energies. Therefore, here just you now tell me which is here number of holes electron is very much larger when compared to number of holes in the valence band. Therefore, the electron energy is more. Okay, number is more, therefore electron energy of the number of electrons is more when compared to the energy of holes. Therefore, definitely Fermi energy level will be shifted here towards the conduction band. So, this is the Fermi level. Are you following? Therefore, Fermi energy level will be definitely shifted. It will be going at the intrinsic semiconductor means it will be exactly half the way. But here it will be just, where is it? It will be shifted towards the conduction band. Okay, therefore just slightly below the donor energy level it will be. Are you following? If the concentration, see for example, if the that very much depends upon the concentration of the impurity. If the impurity atom, concentration of the impurity atom is more, then even Fermi level sometimes it may go inside the conduction, it may fall in the conduction band, inside. Why? Because you know very well, center of gravity, center of mass will be closer to the heavier center of mass of two particle system. Okay, it will be closer to the heavy mass, right? Like that here, whichever is here with respect to energy, I told you it has to be weighed with respect to energy. Okay, center of gravity in accordance with the energy. Therefore, here energy here for electron is more. Okay, therefore, if more number of impurities added, therefore energy will be very large. Therefore, it will be sometime it may even fall into the conduction band. Okay, but actually as such it is for intrinsic it is half the way. Now if it is by N-type it will be shifted towards the conduction band, right? Now this is about what is that? N-type semiconductor. Are you following, children? So this is here majority carriers are electrons and minority carriers are holes. Okay, right. Now let us go to the next one. Now let us go for, okay, I think I just want to yeah, in the previous one itself I just want to tell you something else. See, oh. Yeah, here you see because it's very colorful I thought of showing it. You see here, this I want to highlight it. See, in the case of p-type you see the bond it is given by 2 like that. See here the electron, these are all electrons, these are all electrons. Okay, this is phosphorus. Here I have taken arsenic, here it is phosphorus. See, it has 4 electrons are engaged in forming the bond, but 1 electron here, free electron. How it is colorful now? This I thought, okay, let me show it to you. Okay, this is one. And one more thing, here you see, I just want here, see 5 pentavalent impurity, so 5 electrons. Here it is tetravalent. Therefore, 5 out of 5 electrons, 4 electrons are engaged and 1 electron here, it is free. Okay, therefore, unbonded free electrons donated by the pentavalent atom. Okay, this also, just because I just want to show it to you. Anyhow, everything is discussed anyhow. And one more, see, This is a conduction band, this is a valence band. Here you see your donor energy level, it is just below the conduction band, and Fermi level is also closer to the conduction band. Therefore, this is about N-type semiconductor. Now let us go for the next one is, we'll go for P-type semiconductor. Okay, in the case of P-type semiconductor, see what is happening here is, in the case of P-type semiconductor, see it is here depending upon the impurity what you are adding. Now we are actually categorizing into N-type and P-type semiconductor. And here in the case of in the case of P-type semiconductor, okay, to the pure semiconductor, trivalent impurity is added. Trivalent impurity is added. Okay, so trivalent impurity. Trivalent impurity means what is that? Indium. Okay, indium, boron, aluminium. Okay, aluminium. And even gallium, okay, etc. etc. These are all trivalent impurity. Okay, so when this trivalent impurities, any one at a time, see either indium or boron, anyone. Okay, so when a trivalent impurity is added to the pure semiconductor, the tetravalent semiconductor. Okay, therefore what will happen? Now we are going to see here. See, I think I will use this one only, okay, to explain. You see children, here what will happen? See here it is boron. It is taken as boron. See, boron, there are only, it has trivalent, 3 electrons are only there, whereas silicon is having 4 electrons, of which, see, boron 3 electrons are very much engaged in forming the bond, covalent bond with the neighboring silicon atom. But here you see there is a vacancy. This is a vacancy. It is not filled because boron has only 3 valence electrons. Okay, so, but what there will be some hole. How nicely it is given, shown, you see, hole. Okay, and this hole, okay, what it will do, therefore, it accepts the electron from the neighboring silicon atom. Therefore, this electron will jump here, thereby creating the hole here. Then it will jump from the nearby here, from here. Okay, like that the hole will be actually moving. When you are, therefore it is actually speaking, okay, this hole is, one extra hole is produced when you are adding a trivalent impurity to the pure semiconductor. Okay, so this, how it will contribute to conduction, because once it accepts the electron, that is why it is called acceptor impurity. It is very much ready. Here there is hole is there. It is very much ready to accept one electron. It accepts one electron. Because when in the case of pure semiconductor, there is no vacancy at all. See, actually speaking, what is that? All the 4 electrons are engaged in forming the covalent bond. Okay, but here, when you are adding trivalent impurity, because it has only 3 electrons will form a covalent bond with a nearby atom. But there is one, it is deprived of electron here. That is a vacancy. And that vacancy will be filled just by accepting the electron from the nearby atoms. Therefore, that is why it is what is called acceptors or acceptor impurity. Okay, the trivalent, what is that, indium, boron, gallium, aluminium, whatever is that, this is what is called, what is that, acceptor impurity. Trivalent impurities are called acceptor impurities. So that what it is giving one extra hole for conduction. The holes are moving now nicely, which means the holes are in motion. Extra one hole is created here. Okay, therefore, you know that these holes correspond to holes will be there only in the valence band, correct? Holes are associated with the valence band. So, these holes, therefore in the valence band, there will be, what happened, there will be, this will be associated, this hole will be associated with the valence band. Therefore, already there will be intrinsic characteristics is Ne that is equal to NH. Okay, Ne that is equal to NH. Why? Because at room temperature, some of the electrons from the valence band will jump into the conduction band. In addition to that, in the valence band, there is one more, what is that? Vacancy hole is created because of the acceptor atom. addition of acceptor atom. Therefore, here you can say that NH, number of holes in the valence band will increase. It will be more than number of electrons in the conduction band. Okay, therefore, number of holes I told you already in the previous class, holes take this portion of seat of positive charge. Okay, therefore, positive charge holes are more when compared to the negatively charged electron. Therefore, here positive charges are dominant. Positive charge, okay, holes or majority carriers. Why? They are very large in number. That number of holes, extra holes, Ne is equal to NH is always there. But the extra holes, number of holes depends upon how many atoms you are adding, number of atoms. Impurity atoms, number of impurity atoms you are adding. One impurity atom will give rise to one vacancy, one hole in the valence band. Okay, therefore positive charge holes are majority carriers, and electrons, that is why it is what is called majority carriers. They are only meant for conduction. They are dominant here. Okay, therefore that is why it is called P type. Positively charged are dominant, therefore it is P type semiconductor. Okay, therefore now this is very, very important. And now let us go for, see here, this with respect to this diagram, this is also, see, now how many here, the trivalent impurity has only 3 electrons. Therefore here, and all silicon and germanium 4 electrons. So here it has one hole here. So these 3 electrons are engaged and one hole. Okay, and this hole will be readily filled with the electron from the neighboring atom. So the holes will be moving. Okay, so they are mobile. Holes are mobile. Holes in the valence band are mobile. Okay, very much. They are only contributing what is that, conduction. They are the current carriers. Holes in the valence band and electrons in the conduction band. Okay, therefore now let us go for, now you see, I think let me explain with this only. Now where will be, now I just want to, because you know that, okay, let me draw here, conduction band is there and valence band is there, and here this holes which are created here, extra holes which are created because of the addition of trivalent impurity. Okay, they, see where, see here, this is your valence band and this is your conduction band. Okay, and because of thermal excitation there will be, what is that, 1 or 2 holes will be produced in the valence band, and thus that many number of electrons will be there in the conduction band, that we know. But in addition to that, when trivalent impurity is added, there is some extra energy level will be created. Okay, and extra energy level, where will it be created? The extra energy level will be created just above the valence band. Just above the valence band. This is a conduction band. Okay, therefore extra energy level will be created just above the valence band. What is the, therefore what is the difference? See the energy difference gap. Okay, what is the energy difference between the uppermost energy level of the valence band and this energy level is what is called acceptor energy level. That is donor energy level in N type. Here acceptor energy level is in P type. Okay, therefore it is what is called acceptor energy level. What is the difference between these two? This is, for silicon it is 0.045 electron volt for silicon as usual and 0.01 electron volt for germanium. The gap, okay, the gap between the acceptor energy level and the uppermost energy level of the valence band, that is there, no, that is 0.045 for silicon, 0.01. Therefore what happens here, these, what here there are so many electrons are there, no, isme to electrons, it is filled with electrons, no, so there also I have to draw here. See, okay, I'll do like that. So here these electrons, all these electrons, what they do, because there is no need for them, these electrons to jump to conduction band now. Why? Readily acceptor energy level is there, it accepts. Okay, you come here, electrons. Electrons, if the electrons are coming here, see all these electrons will be, what they will go do? They will be jumping here into this energy level. Are you following? Nicely, they will jump. All these, why, which level? This level. Why? Because it is accepting the electrons, na? Therefore, you will be getting all this here, see? Now, therefore, from here it will jump. Okay, and it will be available in the acceptor energy level. Thereby, this will become, once it is jumping there, now it is no more the electron, but it is nothing but a hole. Extra holes are produced. Here, after jumping, it becomes a hole here. Okay, therefore the electrons will readily jump into the acceptor energy level, thereby, what is that forming? Thereby forming extra number of holes in the Kunsa band valence band. Are you following? So now all the electrons will be, why to go to the conduction band? Conduction band is far off, no, this much energy gap. Okay, therefore, this much energy gap at room temperature it is not possible. All the electrons cannot jump. Only some electrons may jump, that is why they are available here. Apart from that, electrons, the lowermost energy level of the valence band, they can readily go to the acceptor energy level, thereby forming the holes. Okay, therefore, this is acceptor energy level. In the case of p-type semiconductor, acceptor energy level will be created just above the valence band. Okay, so that helping the electrons from the valence band to jump into that level, thereby creating so many number of holes in the valence band. Is it clear? Right. Therefore, now what do you say about the Fermi energy level? Fermi level. The Fermi level here, see, you know, number of holes here is more than, very much larger than number of electrons. Therefore, energy for holes will be more when compared to total energy of holes will be more when compared to that of electrons in the conduction band. Okay, holes in the valence band are dominant when compared to electrons in the, so the conductivity here is dominated by the positively charged holes. That is why it is p-type. In the case of n-type, its conductivity is dominated by the negatively charged electrons. Okay, that is why it is called n-type semiconductor. Here it is p-type semiconductor. In the case of p-type semiconductor, then total energy of the holes is more when compared to that of electrons in the conduction band. Therefore, definitely Fermi energy level will be. Now, Fermi energy level will be, where it will be? It will be somewhere here. It will be shifted. Okay, towards the valence band. It is the Fermi level. In the case of n-type semiconductor, it will be going towards the conduction band. But in the case of p-type, because here dominant is negatively positive charge holes, therefore in the valence band, therefore Fermi level will be shifted towards the valence band. Is it clear? So this is about p-type semiconductor. Okay, therefore what is, let us go for, what is the difference between, shall we go for now, difference between both the kind, that is n-type intrinsic and the extrinsic semiconductor. See, intrinsic, the case of intrinsic semiconductor, intrinsic and extrinsic semiconductor. Okay, what are all the differences? Okay, now if you see, number one, it is a pure semiconductor. Number one, it is a pure intrinsic semiconductors are pure semiconductor. Okay, but here extrinsic semiconductors are not pure semiconductor. They are actually deliberately some impurities added in type, that is either pentavalent or trivalent impurities added. That is number one. I think you can write afterwards. Okay, now number two, example for pentavalent here. Therefore, here example here is pure silicon or germanium here. But here it is, you can say that silicon and germanium is added with pentavalent arsenic antimony means n-type, and indium boron aluminum means it will be n-type. Okay, therefore that is extrinsic semiconductor. Right, then here number of free, in the case of intrinsic semiconductor, number of free electrons will be exactly equal to Ne. But here, depending upon the type, if it is n-type, Okay, Ne will be larger than NH, and if it is p type, okay, NH will be larger than Ne. Therefore, that is the case, right? Number 3. See, its electrical conductivity is very low. Conductivity is low. Electrical conductivity. Conductivity is very low. But here, it is conductivity is high. But here it is high. Conductivity is high. Okay, right. Then next one. So I'm not writing anything. You have to write. Okay, I'm just okay. Next one. Here, electrical, very important. Electrical conductivity is the function of temperature only. Only temperature. Intrinsic semiconductor conductivity is the function of temperature. Okay, but here, what is that? Apart from temperature, of course, conductivity depends on temperature. Here also, more the temperature, more will be the number of electrons jumping from valence to conduction. But in addition to that, it depends very much on the concentration of impurity. Okay, in addition to temperature, there is no, so it depends on temperature. It also depends on, what? The concentration of impurity. Concentration of dopants added. Okay, so by changing the concentration, you can change the number of carriers. That is a very important one here. Okay, so that conductivity, as you want, you can change the concentration, right? Then, okay, N-type and P-type now. N-type and P-type, it is N-type. Now, N-type semiconductor and P-type semiconductor. Okay, N-type semiconductor means what is that? Pentavalent impurity is added to tetravalent, and P-type is trivalent impurity is added to the tetravalent silicon or germanium. Okay, and here it gives the extra electron. Every impurity added gives one extra electron. Here every impurity added gives one extra hole in the valence band. Here extra electron in the conduction band, N-type, extra holes in the valence band. That is the second one. Okay, first one. Second one is, what is that? Therefore, third one, you can say that Ne is very much larger than NH, and here NH is very much larger than Ne. Okay, right. Therefore, that is majority carriers. Majority carriers here are electrons. Majority carriers in P-type is positively charged holes. Okay, then next one. The donor energy level here, about donor energy level. Donor energy level is created where? Just below the conduction band, right? Here, acceptor energy level is created just above the valence band. Acceptor energy level is created just above the valence band. Next one, Fermi level. Fermi level, okay, lies between the, where actually it between the donor energy level, actually the Fermi energy level, it lies between, okay, it is okay, it is not for donor energy level will be very much below the conduction band. Here acceptor energy level will be just above the valence band. Actually, you see, it is shifted towards the conduction band. Here it is acceptor energy Fermi level here. Sorry, donor energy level we have already given. Fermi energy level. Fermi energy level is now near the conduction band, but here in the case of P-type, Fermi energy level will be near the valence band. Okay, that is it.